Greetings A-level chemists, welcome to a little video where we're going to talk through aldehydes and ketones and have a look at some questions. So, we have to write a balanced chemical equation for the following process, the reaction between propanal and Tollens reagent. So remember that Tollens reagent is ammoniacal silver nitrate, so linking it to transition metals, it's this complex where we've got some amine ligands coordinated to the silver center, and we've got NO3 minus just balancing that charge. And this is done in alkali conditions as well. And propanal, that prefix prop means we've got 3 carbons in a row, and the aldehyde group can only go at the terminal part of the molecule, and it's CHO. And then remember that this Tollens reagent is an oxidizing agent. It itself gets reduced, and to represent an oxidizing agent, we're just going to use square brackets and O. So the propanal goes to propanoic acid, and then literally just count atoms. We've added 1 oxygen, so we need 1 equivalent of the oxidizing agent. And there you go, with square bracket notation. If you want to look at this in a little bit more depth, I mean, it's rare that you're going to be asked this, but if we have a look at it in terms of oxidation states, so we can write C3H6O being oxidized to this carboxylic acid. Now, under alkali conditions, this is going to exist as the propanoate ions. It's going to be C3H5O2 minus. So on the left hand side, we know that oxygen is -2, and we know that hydrogen is +1, and there are 6 of them, so we've got a total of 6 negative charges. So we can say that the carbons have a fractional charge, but they add up to a total charge of -4. And then we're going to do the same thing on the other side. So 2 lots of oxygen is going to be -4 in total. Remember, the oxidation state is actually -2 twice, so -4. The hydrogens give us a total positive charge of +5, each one being +1. And then, now just have a look. So what I'm thinking is, we need an overall negative charge on the carbons, and that has to be -2. And the reason for this is, -2 minus 4 equals -6, and then -6 plus 5 gives us the overall charge of -1. Okay, that looks good to me. So then let's have a look at how the oxidation state changes. So in total, we go from -4 to -2. So now you've got to think, is it going more positive or more negative? Well, it's going more positive by 2. So in total, this is a 2 electron oxidation. Okay, if you look at -4 to -2 on the number line, it's definitely going more positive by 2. And that difference is the number of electrons it has lost. Okay, so then if it's in alkali conditions, we've got 3 negative charges that we're going to balance with 3 hydroxide ions. So then let's have a recount. So we've got 3 hydrogens on the hydroxide. Okay, so how many hydrogens do we have on the left hand side? So in total, we've got 9H on the left hand side, and we've only got 5H on the right hand side. Okay, this is good because then I need 2 molecules of water, he says. Let's see if this works. So then 5 plus 4 takes me to 9. That looks good. 9 hydrogens, and then got 3 carbons and 3 carbons, all good. So I've got 4 oxygens in total, and I have 4 oxygens in total here as well. So that looks good to me. That looks good to me. So there is my oxidation reaction, and I also need a reduction reaction, and that is where we look at my ammoniacal silver nitrate. So what does that species look like? So let's write down Ag, and we've written the formula up there anyway, so it's NH3 2 times with a plus charge. Remember that the silver has the plus charge because the ammonia ligands are neutral, so then we need a 1 electron reduction to form metallic silver and 2 NH3. Okay, so then what do we need to do to this? Remember, the oxidation is a 2 electron oxidation, so this needs to be a 2 electron reduction, so we're just going to scale everything up. And that becomes 4NH3, so the combined equation is going to be, cancel the electrons out, this. But I'd be very surprised if you get something like this. Okay? I mean, nigh on impossible, but who knows? You never know. Okay, and there you go. There is my combined equation. All right, let's have a look at a follow-up question. And the follow-up question here is the reduction of propanone. So now we're looking at ketones using sodium borohydride, which is a good reducing agent. Okay, and we've got to have a look at the addition of acidified KCN to butanone. All right, not a problem. So we need to write equations for these. So propanone, CH3CO, CH3. And what I'll do is, I'll do a mixture of displayed and condensed. So we're going from propanone and we're reducing it. So this is a source of H- ions, the borohydride. And if we inspect this, that carbon is going to be delta plus and that's going to be delta minus. So my hydride ion is going to attack there. And that C double bond O is going to break. It doesn't ask for the mechanism, but it just helps me visualize what's going on. So I'm going to get a hydrogen attached there from the borohydride, and I'm going to get a hydrogen attached here. So then, just getting rid of that, let's just literally think how many hydrogens we've attached. So we've attached one here and one here. So we're going to represent the reducing agent, which is sodium borohydride, as square brackets H. So let's put square brackets H and then literally add how many that we've attached. So the answer is 2. So we just put a big 2 in front of it. That's it. Okay, so for number 2, we're reacting butanone this time. So CH3, CH2, COCH3, and then we are going to, what are we going to? Acidified KCN. So we're going to get a nucleophilic addition here. So we're going to get a hydroxynitrile. So then just literally inspect what have we added onto the double bond. We've added an H and we've added a CN. So I'm going to need some HCN. Don't need to draw it like, you can just put HCN. Okay, sorted. Okay, thank you for watching. Hope that was helpful. See you later.